Okay, hello everyone, and welcome back to MOPA for this semester. Our first talk is from Fedor Pakhomov from Ghent University and Steklov Mathematical Institute on finitely axiomatized theories lack self-comprehension.
Okay, yeah, thank you. Thank you for the invitation. Yeah, okay, I should first tell that essentially this talk will be the same that I gave in this conference in Wuhan. So there was this proof theory conference. So for people that were there, I'm sorry. So it will be basically the same. Okay, and second, yeah. So I think actually I will not really talk about models of Peano arithmetic in this talk, so it's everything. But yeah, okay, let's start. Okay. Yeah, so essentially, there is so today we'll be talking about so our recent joint result with Albert Wisse. And in fact, in certain sense, the result is very close to second completeness theorem. Namely, it will, in certain sense, it will be a generalization of second completeness theorem. But okay, let us clarify more on this. Okay, but so let me start with some this modern version of second completeness theorem, namely, this strong version of second completeness theorem proved by Pavel Putluk. Namely, it states that no consistent recursive enumerable extension T of Robinson arithmetic could prove its own consistency. Yeah. So the result. So what is actually important here? So of course, Robinson arithmetic is this really weak system of arithmetic where it's basically Peano arithmetic from which you have dropped all induction, right? So basically, you have defining axioms for all arithmetical operations. Basically you need to know that any number is either successor or zero, but not both. Yeah, and that's basically it, right? So it's very weak system, and for all its extension, so no extension of the theory could prove Conti. And Conti here is taken in the sense of this standard arithmetization. So yeah, so basically just writing down this pi1 formula that expresses Conti over some stronger system, where you could make sense of this, so something like S12. And then yeah, and then you just use this formula here. Okay, so this is the result. In fact, it's even so. Dan Willard had done some investigation on this boundary. Basically, what you actually need to have second completeness theorem in this form. So if theory, so basically, on probability of the standard consistency. And basically, what is important is totality of successor function. Yeah, so basically, if so you could even slightly weaken this Robinson arithmetic Q, and so that you will have the system where addition multiplication are just predicate, but you still have totality of successor, and yeah, and this is still enough to provide the same kind of result. So Dan Willard have actually proved, gave some examples of theories without total successor function where this fails. Yeah, so the theories prove their consistency. Yeah, okay, so let me advertise one of my previous results. So yeah, so actually, yeah, so basically this example provided by Willard, they were kind of, basically based on this fixed point theorem, but you actually could so basically what I mean is that so there was this weak arithmetical theories where one of the axioms were defined using Gödel's fixed point lemma. So it's kind of a self-referential axiom. But you could, I think you could do without it. So you could see this theory in the language of set theory with one additional unary function. And so basically what this theory states that so this function v bar is simply function that maps x to the least level of cumulative hierarchy that contains x as a subset. Okay, and there are some basic defining action for this. And so models of this theory are levels of cumulative hierarchy that actually could be successor levels. I mean, standard models. Of course, there are non-standard models. Basically, there is non-standard models also looks like these levels of cumulative hierarchy, but just non-standard levels. Okay, and actually, this holds for this theory, right? So basically, in this theory, you could say embed a predicate version of language of arithmetic. And it actually proves its own consistency, and furthermore, it proves consistency of itself plus statement that all individual ordinal exist. Okay, anyway, so just talking about the state of the art, about this, about equal second completeness theorem as the result about non-probability of consistency, and where exactly the boundary lies. Okay. So now actually let's go to the direction of this particular result that I'm talking about. Okay, so given a theory T that is finitely axiomatizable, let us consider theory of predicate comprehension over T. This will be two-sorted theory where you have sort of individual objects and the sort of sets. Okay, so basically we have all symbols of the signature of T now acting as symbols on the sort of sets. On the on the sort of individual objects. And finally we have membership predicate. So basically, if you have seen theories like AC0, so it's like something like AC0 by this relativized setting, right? So basically, you have so we have individual objects and then we have sets. And the main axiom is this axiom schemata of predicate comprehension. So it states that we have comprehension for formulas without second-order quantifiers. So everything is very natural. Okay, and the point is that it's quite easy to see that it's always a conservative extension of T. And for this, you could use a very simple model theoretic argument, namely, namely, you just consider a model like this, or something like. Given if model M satisfied T, then of course if you consider the model when this M is still corresponding to sort of individual objects, and then you add to this and you interpret this sort of sets as just definable subsets. First order definable subsets, then this thing will satisfy theory of predicate comprehension over T. And so this basically by this argument, it's very easy to show that we have conservativity. Okay. Okay, so now going to our main result. Sometime before, so Albertista proved this beautiful theorem that no consistent sequential finitely axiomatizable theory T could interpret its own predicate comprehension. And so now so our result is basically that we have managed to extend this to all theories. Now, before there was this side condition that this basically it worked only for sequential theories, and the point is sequential theories are essentially, in a sense, like arithmetic. So there's also theories that could talk about internal finite sequences, and in the end, you get that basically up to interpretability. Any theory like this, for example, it's interpret Robbins arithmetic Q. So basically, this is already this. We are living in this. So we're talking about sequential theories. Essentially, we're already talking about this. In a sense, theories containing arithmetic. But when we are going to arbitrary theory, of course, we don't no longer have any kind of arithmetic necessarily internally. So this could be really arbitrary. Okay. So yeah. So this is the result. So now let me discuss why exactly, how exactly this result is connected to secondary completeness theorem. Okay, so I think this the situation where the connection is most transparent is actually not the case of the usual predicate comprehension as defined before for finitely axiomatized theories. However, in the case when we the schematic predicate comprehension, and now, namely, idea is the following. Now we consider theories that are axiomatized by schemas. So yeah, so as usual, schemata by schemas, I mean the following. So we have this. So we have some some formula with free predicate letters, and then instance of the schemata is the result of replacement of these predicate letters with arbitrary first-order formulas. So particularly by schemas, I mean schemas where this the substituting formulas could be arbitrary. So of course, sometimes when we talk about schemas, we're talking about this restricted schemas. So you're talking about, say, I don't know, something like, for example, an implementation of AC0, you don't talk about, say, arbitrary formulas, but we're talking about formulas without second-order quantifiers. However, this is not valid schemata in the sense of what I am talking about now. And the valid schemas are only the ones where you substitute arbitrary formulas of the language. Okay, so as I basically prototypical example of a theory axiomatized by finitely many schemas is the Peano arithmetic. Of course, we have a bunch of basic axioms, plus we have induction schemata. So this basically, yeah. So this we have one schemata of induction, and then we substitute arbitrary formulas for which we could perform induction. Okay, and again, by more or less trivial model theoretic argument, one could show the conservativity of this schematic version of predicate comprehension. So by schematic version of predicate comprehension, I mean that we, in addition to predicate comprehension, as defined before, we had universal closures of schemata. So basically, before we have this arbitrary substitute, result of arbitrary substitutions of sets of formulas instead predicates and schemata, and now we are allowing this quantification over this predicate letters. Yeah. And this is will be this schematic version of predicate comprehension. Yeah, and so again, so by the same kind of model theoretic arguments that we seen in the last slide, we could prove conservativity of schematic version of predicate comprehension over base theory T axiomatized by finitely many schemas. Okay, so now consider some examples, and the point is that some well-known theories are precisely of the form, namely AC0 is schematic predicate comprehension over PA, and at least, okay, with knowing deterministic theory, you maybe need to be more careful. But basically, it's essentially else the schematic version of predicate comprehension, but now over thermal-Fraenkel set theory. Okay, so yeah. So of course, this schematic predicate comprehension is something that we all have seen. Now let's discuss how it's connected to predicate comprehension. So okay, so for simplicity, I will be working in this most strong case, so overextension of Thermal-Fraenkel set theory, but in fact the same could be done with PA and correspondingly AC0. Yeah. So okay. So basically, observe the following connection, namely that given this, if you have two theories, axiomatized but finitely many schemas, then one theory interprets schematic comprehension of other theory, if and only if the first one proves consistency of the other. Right. So basically, what we see here is that the probability of consistency is the same thing as interpretability of schematic version of predicate comprehension. Okay, and hence, of course, this means that at least in this setting, there really not that much difference between the results about non-interpretability of the schematic version of predicate comprehension and second completeness theorem. Okay, of course, this is all claims about this, say, informal equivalence of two theorems. Of course, this is yeah, it's never completely clear because we still need some kind of, because of course, second completeness theorem is simply true. And so we are just talking about equivalence of things that are true. However, the point is that argument here, it kind of have really nothing to do with how second completeness theorem is proved. So in a sense, yeah, this reduction of one result to another, yeah, at least to some extent establishes the informal equivalence. Okay, nonetheless, so okay, let me briefly sketch the proof. Okay, so one direction is really simple, namely the direction from the fact that if theory proves consistency of T, then it also interprets predicate comprehension. Namely, this is simply a formalized completeness theorem. So assuming that S proves con T, there is internal model of M. Internal model, so inside S, we could prove a distance of model M of T, and thus we could construct internally this model of predicate comprehension by a standard construction. And we are done. Okay. And so basically, if we want to do this more carefully, so that this model should be definable by a fixed formula, yeah, so this gives an interpretation. Okay. As the direction is slightly more complicated, okay, so let's business flow. So we assume so that we have an interpretation M of predicate comprehension inside S. Then our goal will be to define full satisfaction class for first order part of this interpretation. So of course, basically this interpretation, since it's interpretation of predicate comprehension, so it's the interpretation of class of basically for Neumann-Gödel-Bernoulli set theory, right? So basically we have the set part and we have class part. And yeah, and the point is that here we could define basically we will build up this satisfaction predicate for first order part to be so basically we want to approximate this satisfaction predicate by classes. inside M. And yeah, and this basically could be done in natural manner using the fact that M satisfies basic comprehension. So basically, if we have this partial satisfaction up to for the first N formulas, then we could using inside this interpretation M using this basic comprehension, we could expand it to one next formula where we enumerate formulas in such a manner so that each formula goes only after all its subformulas. Yeah, and yeah, so basically, there's a very natural way to internally define this full satisfaction predicate, and then given that we have this internal definition of full satisfaction predicate for M, we just prove consistency of the theory T by straightforward induction. So because if you have this so basically truth in particular any satisfaction predicate is truth definition, and this truth definition satisfies T, and so this basically will be a complete consistent extension of T. And yeah, so this implies consistency of T. Okay, so this was kind of easy. Okay, so now let's go to the case of weak theories, where this of course is much more interesting because for strong theories, indeed, so that I mean the gap between the basic comprehension and consistency is really small. Okay, so now finally, so I mentioned this result of Visa about non-interpretability of basic comprehension for sequential theories. So finally, let me define what sequential theories are. So basically, I think people consider a bunch of different definitions of this, but basically always the idea is more or less the same, so that we want to have theories that could internally talk about finite sequences. And kind of one way to state this is to say that that in theory T there is a definable membership predicate that satisfies very rudimentary set theoretic axioms. And these very rudimentary set theoretic axioms are the axioms of so-called adjunctive set theory that states that there exists empty set. So this simply means that exists empty set. And then we could add one additional element to any set. Right? So so basically, yeah. Okay, yeah. So this is really a minimalistic axiom of set theory, but of course, given that, then so with some bootstrapping, you could talk about a lot of stuff. So in particular, this just as adjunctive set theory already interprets Robinson arithmetic Q. And it furthermore interprets even slightly stronger theories. So in particular, the one that will be of interest here is the theory S12. So S12 is this other well-known weak arithmetical system. And so the point is that unlike Q, which is really weak and you couldn't formalize naturally a lot of stuff there, the system S12 introduced by Sam Bass is much more reasonable. So this is the so basically S12 is a theory so where you could talk about polynomial time computations, and essentially its main axioms is axiom of NP induction. So it's kind of a very natural system. So okay, yeah. So when I saying NP induction, one should be careful because one could mean two different things by it. Yeah. Anyway, but the point is, this is kind of this very natural system to reason about polynomial time computable things. And one could formalize a lot of basic stuff there because a lot of basic stuff is essentially polynomial time computable. Okay, in particular, one could say formalize this basic mathematics. I mean this proof theory part of basic mathematics. So the notion of proof, the notion of formula, the notion of proof, etc. This kind of things. I don't know. Okay. Yeah, and so there is this result by this is that a stronger version of this proposition about extension of ZF that I have stated, so namely that even over S12 we have the following, so that operatic comprehension of T and S12 plus con T are mutually interpretable. And again, this is basically, so if we take this result, then this of course kind of implies that so what was this result? Second completeness theorem for extensions of S12 is the same thing as non-interpretability of schematic version of operatic comprehension. Okay, of course, for this theories axiomatized by finitely many schematists. Yeah, and yeah. So of course, we have this second completeness theorem for extensions of S12. Yeah, and which in fact could be proved by fairly standard Gödel style proof. Really nothing special about it. Yeah, and so basically with some basically if you arrange this right, then from this you get that no consistent sequential finitely axiomatizable theory T could interpret its own operatic comprehension. Okay, so this was this early result by Wieser and its connection to second incompleteness here. So now let's go to our result and discuss how exactly have we proved it. Okay. Okay. So the result is that to remind you that no consistent theory T could one-dimensionally interpret its own operative comprehension. Okay, so we will be reasoning. So suppose some finitely axiomatizable theory T one-dimensionally interprets operative comprehension of T. So our goal will be to derive from this that T is inconsistent. Okay, so now, okay, basically here is the plan of the proof, and so let me just comment on how this whole thing works from the larger scale, and then I'll say give details for the most important part of the proof. Okay. First, of course, T from this assumption T interprets operatic comprehension of T, it of course follows that we could iterate this construction, right? So if T interprets operatic comprehension of T, hence operatic comprehension of T interprets operatic comprehension of T, and so on. And hence, and then when we compose this interpretation, we see that T interprets operatic comprehension, ends iteration of operatic comprehension of T. Yeah, so one important thing to know here is that, in fact, here we actually treat operatic comprehension as essentially one sorted theory. So, of course, the point is that when we're talking about this many, say, finitely sorted theories, we always could convert them to one sorted theories by introducing this. So basically, if we say things that actually this domain, so we have this one big domain, and then domains of individual sorts are just subsets of this big domain. And so basically, then we think that this big domain is simply disjoint union of domains of individual sorts. And of course, the domain of individual sorts are simply say defined by unary predicate letters. So this is the way how this, we could canonically convert multi-sorted series with finitely many sorts to one-sorted series. And hence we actually could, so this allows us to naturally define what are iterations of predictive comprehension. Okay, this was basically the first thing. It's kind of very simple. So then, of course, so let's now discuss the second point. Okay, so of course, so the point is, and when we have this, say, some iteration of predictive comprehension, so what we have, so this is a theory where we have essentially this individual objects, then we have sets of individual objects, that we have sets that could contain either individual objects or sets of individual objects, and so on, right? So so basically, this is kind of the theory that essentially have access to this finite level of von Neumann hierarchy. Okay, it was not real von Neumann hierarchy, like this hierarchy of predictive comprehension. So I guess it's more akin of to L than to V, but nonetheless. And next, the point is that kind of basically, if you, of course, we could using this set theoretic structure, then we kind of easily could encode tuples of previous levels on some further levels. Yes, so by basically using the standard construction, so you have the say. And so, so in particular, but if you do it in appropriate way, that what you get is that. So if you have this PC to n minus 1 of t, then it's interpret the theory that PC less than n of t, and this is so. The point is that usual predicate comprehension was talking about just unary predicate. And this PC less than n of t talking about the predicates of different arities up to n. And this, of course, is achieved like this. So basically, we have one level of predictive comprehension on very top, and below it we encode n tuples, more precisely, tuples of all sizes up to n. And then using this kind of set, we could encode this so basically sets. Sets of n tuples, or in other words, predicates of arities less than or equal to n. Okay, so this is basically quite simple. Yeah, so the point 3 is essentially most important one. And what's happening here is that. So basically, appropriate theory PC less than of t. In fact, yeah. Okay. So this, in this theory PC less than of t, there's basically this distinction between small sets. And big sets, and so basically, and so the way how we could internally define small sets is the following. So namely, we consider sets that are domain of internal interpretation of t. Yeah, and the point is that. Okay, the domains of this internal interpretation of T, there are of course large sets, and then there are small sets that are non-domains. Okay. Okay. No. Okay. But the point here is that basically we have this distinction between kind of small sets and large sets, and the point is that universe of small sets is closed under under additions of elements. Okay, and now basically using this, we could go to the case of sequential theory. So this is happening in this item 4. Yeah, so now what we are doing is something like this. So we are using the fact that we have the small and large sets to internally in the PC less than of t define forcing such that it forces t. So basically, so by forcing we define additional membership predicate that satisfies this, axioms of adjunctive set theory, and hence we're getting to the sequential situation. Yeah, and so I will talk more about this later. Okay, and using this is it's fairly easy to finish the proof, right? So then so then some kind of iterating this construction with this comprehension. So we could go from forcing interpretation of t plus is to forcing interpretation of pre-comprehension of t plus is. So basically, because you kind of could combine these forcing interpretations with pre-comprehension. Okay, hence what we see is that pre-comprehension of t plus is forcing in t, and hence it's interpreted in t plus is. And so we are essentially, and then thus we are essentially getting to completely sequential case. So now the only difference from the usual situation is that instead of talking about situation when sequential theory interpreted, we're talking about sequential theory that forcing interprets. So, it's on pre-comprehension, but it basically could be dealt with in a standard manner, and then we are just getting into this Visser case. Okay. And this is not possible by the second completeness theorem for S12. And so this is how we are getting to contradiction. Okay. Yeah. So this is just a slide with the theory of PC less than t. So as I was talking, basically PC less than t is a theory with where we have not just unary quantifiers over unary predicates, but rather this quantifiers over sets of n tuples. Okay, exactly sets of I tuples for all I bounded by n. And we have a respective axiom of basic comprehension. So this is kind of very straightforward. Okay, so now let me discuss forcing interpretations. So essentially, I think this so here essentially we're talking about say not forcing in set theory, but rather forcing over very big theories, and we don't really need to reconstruct set theoretic axioms because reconstruct this say von Neumann hierarchy, and hence it's kind of much simpler. Okay, so basic premise of forcing interpretation is that we want to so the forcing interpretations are essentially internal formalizations of Kripke models. And hereby, of course, since we are talking about classical theories, essentially, so Kripke model we could just say just identify classical logic with negative fragment of intuitionistic logic. Yeah, and thus, so essentially, we'll be talking about the Kripke models where we are just interested in connectives and not and for all. And then it's got kind of very standard manner could define what does it mean to what is, say, classical Kripke model. So basically you define, okay, so usually you have this set of worlds, then you have, in each world you have domain. Domain should be expanding. And then you should define satisfaction of atomic atomic formulas. So of course, when we are talking, embedding about identification of classical logic and negative frame deterministic logic, we also need to add double negations to atoms. But here we are achieving this by requiring that satisfaction of atomic formulas is such that so basically essentially this condition on free for satisfaction of atomic predicate is the same thing as taking some downward closed set and then closing it under double negation. Yeah. Okay. Anyway, so then we define the satisfaction for atomic of orbital forms defined by straightforward induction in very standard manner, and then so basically okay. So okay, now it's kind of important point in order to talk about forcing interpretation in a series. So we will basically reduce this to talking about just usual interpretation, but of this theory. So namely, yeah. So this theory Km of t. Basically, the theory that it's talking about, whose model are Kripke models for the theory T in the sense. So basically, we have this part of the one sort that corresponds to worlds, other sort that say whose elements are elements of the domains, and then we have this satisfaction of atomic formulas. And then the axioms are the axioms that basically this whole thing is indeed a Kripke structure, and that axioms of T are forced in it. Okay, so basically that's Km of T, the theory formalizing that just the theory whose models are Kripke models of T as structures. Okay, and so basically we say that one theory interprets forcing interprets other if the first theory interprets theory Km of T. Okay, now so let me explain how we actually force sequentiality. And so the point here is that in order to force the sequentiality in straightforward manner, we need to have smallness notion. So basically, we should. So basically, we are linking the theory PC less than 2 of T. So the theory of paths of elements of theory where we have set of elements and set of paths of elements. And what we want is that basically we split unary sets into two groups. So there are small sets and there are large sets. So, and small sets are such that empty set is small, and say small sets are closed under additions of additional elements. So basically, for any small set x, x plus one additional element is alpha small. And so essentially the point is that kind of small set are this. Okay, they in particular should kind of you could think about this sets that at least contain some final set in some sense, and hence the big sets are sets that are in some sets infinite. Okay, but now but basically now having this, it's quite kind of very easy to define the required forcing. Because what we really because as you how usually the simple forcing argument works, we want to define some kind of object from approximations, and now the point is that we have this notion of smallness, we could talk about the small approximations, right? So basically, approximations of our membership predicate on such that that are defined on a small domain. And so, yeah. And so yeah, right. So basically, this binary relations on small domains will be our forcing conditions. And this say order on them will be simply order by end extensions. So yeah, quite naturally, if you want to build membership predicates, so kind of naturally to define to have this order on end extensions. And so the point is that if you just do this thing, so you have conditions are simply binary relations, and your order on condition are ordered by end extension. And so this, of course, this binary relation, we are thinking about them as finite approximations of our membership predicate. So for this particular forcing, we actually in this forcing model actually this corresponding Kripke structure actually forces that this membership predicate satisfies adjunctive set theory, and the check actually is kind of straightforward. Okay, so this is basically the proof. And now the second point is why we have notion of smallness. And okay, so actually I started to explain this in this one of the previous slides, but now let me get in slightly more details. Okay, so now we're working with the theory PC less than n of t, and we want to define notion of smallness for one-dimensional sets. Yeah, so of course, basically, this language, so basically in the theory PC less than of t, we have this n-dimensional sets, and here, so this, sorry, we have the sets of n tuples, we have sets of n-1 tuples, and so on. And thus, basically, when n is large enough, you could talk about this internal models of T. So basically, so the way how we talk about this is kind of easy, namely, T is of course theory in finite signature, or it's even finitely axiomatizable. And so we could talk about interpretation of all its predicates, and the predicates, of course, are interpreted by this sets of corresponding arities. And now, and then we could naturally talk about the axiom of T satisfied in this model. So we just naturally translate finitely many formulas of the language of T into this interpretation of predicates of T by some sets. Yeah, and then our whole formula small of X simply says that there are no model of T such that its domain contained in X. Sorry. Okay, so it should be contained with the domain. Not domain X with the domain contained. Okay. Yeah, and the point is that okay. So talk about this property of smallness. So okay, so property one holds for trivial reason because of course the domain of all sets, so of all elements, for it we have interpretation of T, namely the identity interpretation, and of course we couldn't have interpretation of T on this empty domain, and the domains are closed under addition of one element because okay, the point is that we always will be able to go from interpretation on some domain to interpretation on domain with one less element. Because okay, and this is because okay, so okay, because so we know that T interprets pretty comprehension of T, right? And in particular, this means that T interprets itself disjoint union 1, right? So where 1 is some theory of x equal to f. Let's say. And so the point is that we kind of, if we have interpretation, so and if since we, so this of course implies this, because the point is that this PC of T, it kind of contains domain of T and it contains some non-empty domain, right? So because we at least have at least one set, namely the empty set, and so hence so T interprets T disjoint union x. So basically, so if you have some interpretation of T, then there is some model of T, then there exists this internal model of T, whose domain is not the whole domain. So basically you're taking this interpretation of T disjoint union x of x inside T and applying a particular model, right? So we have this model M, some model M. And so when we're applying this particular interpretation inside M, then we kind of, so what we're getting something, yeah, some interpretation. Okay, this, of course, this domain of this interpretation maybe it still may be whole M, but then it's kind of split in two parts, right? So they're like interpretation of T, interpretation of x equal to x. And hence, basically, we have this internal. If we have model of M on some domain, then we have model of M on domain that contains at least one less element. And exploiting this fact, we could show that basically if some set, so basically if some set haven't supported in the model of T, then a set with one additional element else couldn't support model of T. Okay. Yeah. So and basically there's also basically so the combination of these two things shows us that basically so that we could construct this forcing interpretation of T plus adjunction set theory in basic comprehension of T. And this is kind of really important. And eventually, from this, we construct this thing, right? So T interprets T plus IS, forcing. And this is essentially was the most important part of the proof. The other part is a kind of routine. So this basically finishes the proof. Okay, so now about generalization. So with this, so for multidimensional interpret, so of course this previous theorem was for for one-dimensional case. So of course this theorem is also due to the same authors. Yeah. And okay, so this so basically in multidimensional case, we unfortunately haven't obtained the result that no theory couldn't n-dimensionally interpret its own basic comprehension. However, we show that no consistent theory T could n-dimensionally interpret the theory PC less than n of T. And so this is so basically it's quite kind of easy to derive this result from the previous one. Namely, we could talk about the theory T to n, that is this natural theory of n tuples of elements of a model of T. So this is so basically this is the point of the theory is that the kind of we don't have domain for T itself, but they're like all elements objects in the theory are kind of n tuples of element of objects of T. But then you could put this with some natural signature, and then we have this very natural connection. So if the T n-dimensionally interprets U, if known if this T to n one-dimensionally interprets U. And then applying the previous theorem to the theory T to N, we basically are getting this multidimensional variant of the previous theorem. Okay, and final point. Of course, this forcing argument for forcing interpretation of sequentiality, in this result that I talked about before was completely negative result, right? So because essentially the whole purpose or this whole argument was incorporated in this proof by contradiction. So we assume that some theory that it's operative comprehension, and then during this the fact that this couldn't happen, we basically constructed this forcing interpretation. However, yeah, so essentially the same theorem shows that this could never really happen. However, basically we could extract this argument and see what positive results does it give. Okay, consider the following theory: the theory of adjunctive classes, and this is this theory is kind of extremely minimalistic class theory. So we have this axiom of empty class, and we have the axiom that we could add to any class one additional element. Okay, in the case of when we have this AC less than n, so we have this classes of n tuples, and hence we are adding one tuple, and we have the axiom of empty class consisting of no tuples. Okay. Yeah, and so now this first positive result is this one. So basically consider the theory of adjunctive classes of arity of at most 2 with no universal axiom. So the axiom that says that so there are no universal class. So in a sense, like I guess in this case it would be better to call this not classes but like sets, because usually with classes we have universal class. Anyway. So basically this very minimalistic theory for forcing interprets T plus adjunctive sets. So essentially from just these classes we reconstruct much more powerful structure of sets that could contain other sets. Of course, with classes there's major limitations, so classes couldn't contain other classes. Okay. So second result that follows from the previous one is the following. So suppose some theory T one-dimensionally interprets itself on domain that doesn't coincide with the class of all objects. So essentially the same thing as we seen before. This interpretation. So this is condition the same thing as this, right? So that there is interpretation of T in T that with some whose domain is not the whole initial domain. And then for this kind of series T, the theory AC less than 2 of T forcing interprets T plus adjunctive set theory. Yeah, and so and finally, also basically if we have some theory that is so it has interpretation of adjunctive classes for itself, then the theory interprets T plus forcing interprets itself plus adjunctive sets. Yeah, so basically what this shows that is that this of course this notion of sequentiality, when it was considered in the set with usual interpretation, it was a bit restrictive, but here we see that it's kind of so at least with this forcing interpretations we could we could say get sequentiality in very so for a lot of different theories. So this is kind of really big conditions. Okay. Okay, so that's all.
Okay, thank you, Fedor. And if you like, you can unmute and clap if you like, or you can use the emoji. So thank you. And I think we have time for some questions. If anyone has them, I'll see. Let me open up the gallery and see if anyone is begging to speak.
Okay.
I don't see anyone. Anyone can jump in if you have anything.
Well, I can ask a question, but I don't know whether as a co-author that's okay. So can you go to this back and forth interpretation from AC smaller 2t plus this infinity axiom to NT plus AS?
Sorry, you mean the last slide, yeah?
Yeah. Yeah. Okay. So so these effects, I think the result is much better than stated, because it's not just that there is a forcing interpretation, but also you can also go back, of course, from P plus AS. We can ordinarily interpret the theory AC smaller 2, etc. And but I think the real important point is that these are also very good interpretations, right? So they really keep T untouched. So they are not like they are not like Henkin interpretations or anything.
Yes.
Thick.
Yeah.
But
yes.
My question is, could we hope to extract more information from this, right? Because they're so. It's a good notion of sameness between these two theories that we have there. It's not by interpretability, so it's not that good, but it's still something good.
I mean, yeah. I mean, this is kind of feels like that it's something that I would call, so that this T plus IS and kind of obtaining this forcing definitional extension, right? So basically, we are preserving domain of T.
Yeah.
And in fact, we could even say key in this, say somewhere here, for example, right? So we could even keep classes, right? So the only thing that we are defining this new membership predicate for our cumulative for our adjunctive set theory. I think we just never really tried to work this out, but I mean, probably you could say try to do the same kind of to try define categorically this notion analog of by interpretations, but for forcing interpretations, right?
Right, sure.
So we need to,
some
of course,
sense.
of course, like Andrew. So of course, since I think it's a bit more tricky what exactly are morphisms of interpretations between interpretations. So yeah, okay. Anyway, yeah. So this. But as soon as we say have a good notion of two categories of forcing interpretations, then of course we will have notion of this forcing by interpretability. But yeah, I mean, but I never looked into it really. So,
but also I'm not sure. I don't dare to predict that this would actually be a case of that, right? Because you're for example, if you go from T plus AS backwards, you have different choices for defining your finite or Schmeinite sets there, right? So it's
no, I mean, if you're talking about this first theorem, then I think okay, in second theorem it's a bit more tricky because like there again, so we're kind of forgetting about large sets in the second theorem.
Right.
But in the first theorem, I think we essentially, so what's happening, I think that the domain of, so basically classes that we obtain okay, maybe one need to be more careful if you here, but I think if you could, maybe we probably we need to play around with this, but yeah, so, because I probably here if you do it like right now, like we're doing right now, you not necessarily fully recover these binary predicates, binary classes. But I mean, if somehow we say, for example, if we require that binary classes, all binary classes are classes whose domain is unary class. Maybe because when we yeah, I don't know. So,
because I get, well, still one remark about this. So the theory to the left. So if you think about T plus AS, right? So this has all kinds of, so you allow that there are circular epsilon chains, etc., right? So this is still a kind of wiggly, scary theory, where the other one is, okay, well, we simply extend the given theory with Schmeinite or finite sets, and that's it, right? There's no circularity. It's really extending it with classes, and so there you don't have a funny business there. So in some sense, this sameness between these theories gives you the hope that the theory to the left could give you insights about the theory on the right, because the theory to the left is so much neater.
No, but I mean, of course, the point is that this result is not that precise, right? So because in reality, so of course we are not completely describing what our this forcing interpretation really gives when it's writing the theory to the right. So we're just writing this what we want to say, minimalistic things that we want for the sequentiality. But I mean, if we say really refine this result of this kind, right? So we really say, I think it's possible to get to be in some sense reversible. But yeah.
Okay, thanks.
Okay, so I think let's thank Fedor again. So let me put that little emoji up. Thank you so much. That was a great talk. That was a great way to start MOPA for the semester, and I'll stop the recording here.